Swati Gupta. I introduced Swati yesterday, so we're happy to have her back and now actually talk specifically about her work, the title of which will be on ethical machine learning and supply chain. So I think this is going to be a nice continuation of our discussions yesterday. Thank you, Swati.
Thank you, Jan. Thank you for having me here to this fantastic workshop. I'm going to be talking about opportunities for ethical ML and supply chains. I tried to put together a few open questions or some questions to think about in the design of supply chains. And so I would love for this talk to be interactive. So if you have questions, if you want to interrupt me, if you want to ask something, please do so. Okay, so let's start. So I think a lot of time thinking about this. I spend a lot of time thinking about this question. What is the impact of our automated decisions on the welfare of people, on the well-being of people? And that's going to be one of the central questions in the talk. And as you see, in a paper as early as 2017, so a few years back, in Nature Comment, which is one of the foremost journals of science, people try to define what bias is. And this definition is super nice, and so I want to just read it out to you. It's when scientific or technological decisions are based on a narrow set of systemic, structural, or social concepts and norms, the resulting technology can privilege certain groups and harm others. And so the key words to think about here are scientific technological decisions. There is systemic, structural, social concepts, and harm on some groups and benefit to other groups. So let's keep that in mind while we review some of these recent news articles that have propped up in various domains due to some issue or the other of machine learning algorithms. And when I turn my face, the mic doesn't work. So I'm going to be, okay. Amazon bringing same-day delivery to Roxbury. So Amazon was not providing same-day delivery to predominantly African-American neighborhoods. That created a huge outcry, with Amazon receiving letters from mayors of different cities like Chicago and Boston. Rating systems discriminate against Uber drivers. So there are studies on rating systems and how people rate Uber drivers, but don't just rate the quality of their cars, but also rate the conditions, also rate the language, also rate, also get in biases across with other factors which are independent of driving. There are privacy concerns rising. So Facebook lets advertisers exclude users by race. One thing that I found very problematic was it was letting advertisers create ads specifically for people who are away from home. And so the fact that Facebook had that metadata stored about me was disturbing. Google mistakenly tags Black people as gorillas, showing limits of algorithms. Error rates across different groups because of data sizes might vary a lot. And predictive policing has been a huge domain where algorithmic fairness researchers have been producing a lot of results and insights into what goes wrong in policing algorithms. And automated experiments on ad privacy settings. This is talking about job advertisements, which were where more lucrative job ads were shown to male users than female users. And so we see that algorithms are all around us, impacting all different parts of our life and dictating how we interact and what kind of quality of life we have in today's world. And so here are some questions that I want to mention in today's talk. So thinking about ethics by design and not as an afterthought. So I really would like us to shift our view on ethics and not think like, oh, I have a cool machine learning algorithm, and let me now make it even cooler by adding some ethics to it. But really think about ethics by design. And so the first question is on the impact of Byseason data. What is the impact of biases in admissions, impact of biases in evaluations data? How does that affect our hiring decisions? How does that affect our service decisions, as you'll see for the supply chains? The second question is, what does it mean to be fair? Should I have equal error rates across different groups? Well, if I'm predicting chances of breast cancer, I will have a higher prediction for females than males, and that's to be expected. So what is it to be fair in different applications? We'll dig into that question a little bit today. And The third one is on the impact of uncertainty. So we build our systems, we make some assumptions about the models that we're going to incorporate, the models that we believe to be true. When the systems go out in the world, there is some uncertainty, there's some exogenous factors. How do we account for those, and what is the impact of that as it interacts with our decisions? We'll talk a little bit about that. The fourth one is gameability and strategic behavior. So, okay, now we've tried to make our system as fair as possible, but when it does interact with people and users, is there any strategic behavior that we should be aware of, that we should incorporate in our decisions? That's something, for example, I have an example of how sellers trick Amazon to boost sales. So imagine Amazon is trying to get the fairest decisions of all, trying to boost recommendations, trying to get the new sellers up and running, but sellers have a strategic behavior of their own in this market. And so that becomes an important concern. This is something I will not be able to talk more about in this talk. And the fifth one is transparency and interpretability that we discussed a lot in yesterday's panel about how do we make these decisions, how do we make maybe aspects of these decisions very transparent to the users or workers in our company, and how do we make sure that they feel that the practice is fair. An example I have here for supply chains is this recent lawsuit where Chicago sued Uber and Chicago sued DoorDash and Grubhub for deceptive and unfair business practices. So Yelp was also a part. Uber received a lot of slack at some point for hiking up prices when there was a tornado. People boycotted Uber in New York City, I think, for a few months. So these issues are of extreme importance, and I hope after today's talk, you guys are maybe more enthused to pursue these questions. So let me start with Byseason Data. And this is an example that's quite nice, actually. So what Christian Lum and William Isaac did in 2016 is that they looked at arrest records data that Predpol was using. Predpol is a crime prediction software that predicts where crimes are likely to occur again, and so police should patrol those areas more frequently. So what you see circled here is Oakland. That's a heavy density region with a lot of arrests in the past. And so, of course, Predpol, the software is going to predict that there are going to be more crimes in that area. What these guys did was they looked at the healthcare data set, and they saw that drug use was actually pretty prevalent across that entire strip of International Boulevard, even though from the arrest records, it looked like it was just focused in that Oakland region. So what does that show us? It shows us something very simple, that machine learning finds patterns in data, but if you don't have the full picture, if the data collection process is biased itself, then you would learn a wrong pattern, and you would predict using that wrong pattern and reinforce biases in your systems, right? And so what happened with Predpol was, look, arrest records show us that drug use is very prevalent in one of the races compared to the others. But what Christian Lum and William Isaac did very smartly was they looked at the healthcare data sets, and they showed that the trend was actually pretty consistent across the races. And so this gets me to the first question for supply chains. Are there prediction subroutines used within supply chains that are consistently over or underestimating certain trends in the data? For example, what about demand patterns? Is there a reason to believe that we are only able to estimate demand for certain items because these items have never been on the shelves of certain stores, and so we don't see it's all in missed sales, and we don't see the demands for some critical items, and it could be books, it could be medical supplies, and so on. So that's sort of the first question. Any comments, questions? All right. So the problem is that it's not just about biases and prediction or the data and the way it's collected. It's the fact that in our supply chains or broadly in machine learning systems, decisions build on top of decisions, they build on top of decisions. And so if you have a problem in the subroutines that many more decisions are based on top of and optimized on top of, then that can exacerbate inequalities that you have in the system. And that's circling back to Amazon. not providing same-day delivery in certain parts of major cities. So with that, I want to go to the next question on what is fair. And as an example, I'm going to talk about this work that I did with Girija Ranade, who's a faculty at Berkeley, and a bunch of undergrads at Berkeley, super smart 3 undergrads that we met when I was myself a research fellow at Simons Institute. So there was this emergency room, Alta Bates Summit Medical Center, which predominantly served uninsured people of color and poor regions in Alameda County. This was one of the main emergency rooms in that area. And this building was deemed seismically unfit, and the home company, the owning company, Sutter Health, announced its closure. And so people were protesting on the roads, and they were like, please don't close this. That's the only emergency room we have reasonable access to. Everything else is very far off. And so we started looking at this problem, and we asked, is there a fair alternative to this? Right? Now, we've heard from Barry, who's at another talk, that one way to consider fairness is consider to minimize the maximum impact on any group. Remember that from yesterday's talk? Okay. So let's look at what it might mean to be fair in a facility location setting. So you have a bunch of people, there are red dots and blue dots, there is this emergency room and there's some distance, and let's say you have 2 groups of people, A and B. So is it fair to minimize the total distance traveled by any group? Minimize the total distance traveled by any group. Is that fair? It's like minimize the maximum distance traveled by any group. What could go wrong if I look at this objective? Number of people matters. Excellent. So let me make my groups imbalanced, and this is what will happen in practice. You have minorities, you have majorities. Number of group is imbalanced. Let's say they're scattered across. You're basically serving one population, and you don't care about that minority group. Okay, so let's change our fairness metric, and let's talk about minimizing average distance instead. Is that fair? What could go wrong? Ignores the outliers. Thank you, Larry. So if you have one person who's really far off, well, that means everybody else has to suffer because the emergency room is now going to be placed at the center of these 2 clusters. Right? And will you guys believe it? So before I come to the believing question, the question in practice also is not very clean. Should you group people by race? Should you group them by income, insurance status? Because we're talking about health insurance, health access here. So what should we group people by? And can you believe it? In 93, there were 24 metrics of fairness with 2 groups of people. So we saw this, we were like, how are we supposed to select what is fair? And that's a question that can arise in many cases. In statistical fairness literature, people have quantified impossibility results, where they've said, you can't have predictive value parity and positive rate parity together. You cannot have one definition of statistical fairness and another together. What can we say about all of these metrics? So I'm going to come to that question. Let's look at our data. So that's Alameda County, and that's the distribution from census data on this county. And so you see here, when you're working with real data, it's not as clean as group A and group B. There's all of these different groups. There were 7 groups in the data set. I've plotted 4 here. What are these? The top one shows the white population. The second one shows the black population. The third one here shows below poverty line. And the fourth one shows insurance status. And so you see in real data, there are clusters of these population groups. They're not uniformly spread across. They might have clusters, and we know that zip codes actually highly correlate with the demographic profile of any region. That's what the data looks like. And here is the metrics, the set of metrics we considered. So we boiled down to 18 metrics, which are as follows. So min-max with the total or the average with the choice of the 3 groups. The absolute deviation with the min-max average and the choice of the group, and the Gini coefficient with the min-max average, with the total average and the choice of the group. That's still not covering all the 24. It's only covering 3, but we are taking a cross product with total average and the choice of the group. Everyone with me so far? So now what's our objective? Am I going to combine all of these into a big composite objective and minimize that? That's going to like make me pull my hair out literally. So here's what we did. We built a heat map of, for every metric we found the best optimal solution, and we made a heat map of what that best optimal solution, how good it is with respect to other metrics. So we thought about the metrics as, various people who are sitting in an interview panel and they're rating the candidate and saying, okay, I will give so many points to this candidate. And so as you can see, optimal solutions for any one metric here, let's say 16, the approximation ratio is 10.5. This is pretty bad for some metric of fairness, right? And so what we ended up doing was find a Pareto optimal solution, which had a bounded factor 2.8 or something, 2.1.7, 2.3. 2.3 in the worst case compared to any other metric's optimal solution. So we got a Pareto optimal solution that satisfied all of the 18 metrics. And this gives us a nice way to move forward with making sense of like the large literature on algorithmic fairness. Now, these metrics, yes.
Can you repeat the question?
Right. So Achal's question is, what is the process here? So the process here is that for every metric, I'm finding the best solution, and I'm looking at how badly it approximates any other metric. And the star is a solution that's not optimal for any of the metrics, but actually is a Pareto optimal solution and achieves the best bounded factor of 2.3 for any other metric. So the best solution was something that was not optimal for a single metric. The best solution was something that's just good, approximately good for everything else. And that's one solution we could propose, right? But this is with a lambda parameter of 10. So there is some parameter that I've not told you about. So let me talk about that. Efficiency plus lambda times equity. So we had a composite objective where we said we're going to optimize efficiency. So we're going to minimize the total cost of distance to the facilities, the general vanilla facility location problem objective. And we're going to have some factor of equity in it, but it depends on this lambda factor. Now, how do you translate that lambda factor to the mayor's office in Alameda County, which is an office that got interested in the study? So what we did was, as you change these lambda factors, you get different Pareto optimal solutions. So we got these different Pareto optimal solutions, and we made a map of all the policies as we increased lambda. So as you increase lambda, your Pareto optimal solution changes. But overall, we had 15 possible solutions that were all Pareto optimal with varying levels of efficiency and equity. And that gives a nice output to policymakers to then decide what should you actually ask Sutter Health to do to serve this population that is overwhelmingly being served by the emergency room that's going to close in that county. So that gets us to the role of computing. Optimization can help us characterize trade-offs between efficiency and fairness. Can we use our techniques to actually build a portfolio of options that can inform solutions in practice? And the question I think that could be really important for supply chains is to think about the formation of food deserts. Every one of us, often we think about a company and we try to optimize costs for that company. But if you think about the society as a whole, then maybe thinking about food deserts and medical deserts, for that matter, might be a very important question. So I was talking to the CTO of Walgreens, or Walmart, I forget, and they're actually going to be investing a lot in CVS-like pharmacies. And they were actually concerned about creating medical deserts, which I thought was interesting. And so maybe the perspective of industry is shifting on this. And I put in trash dump sites, because often when we think about facility location, we want easy access, we want quick access. And for trash dump sites, the notions of fairness completely change. You want these to be as away from civilization as possible, right? And so it's good to think about facility location, but just even in terms of the application changes the notion of fairness. Okay. Yes? Maybe let me go over because I'm at 9:56. Okay, and so I'll come back to you once I'm through this. So the last one is the impact of uncertainty on groups, and it's not going to be very long. So let's look at this. So there have been a lot of news about inventory routing and, of course, the pandemic delays, but inventory routing delays that have really impacted disproportionately poorer neighborhoods. So these two news articles that I show you here are oil supply and Turkey during Easter in Venezuela. So to understand this problem about why are inventory routing delays impacting poor neighborhoods, we did a quick study with one of my amazing undergrads, Michael Wong, who's now currently pursuing a PhD at UC Berkeley. We looked at census data in Atlanta. That's how it looks like. Atlanta predominantly below the center is poor, above the center is richer neighborhoods, and those are the zip codes that are below poverty line or above poverty line, the blue and the red regions. And we looked at this really simple inventory routing problem. So we have a depot at the center of the city. We want this depot to serve customers who are the census tracts. For instance, some depleting quantity like water bottles. Water bottles levels deplete. You have your vending machines and the truck goes and refills those. And we have these routing constraints. We have truck capacity constraints, user capacity constraints. Every neighborhood is a zip code block that the truck visits, so we pay a cost for that. And the demand is uncertain. So the demand is assumed to have a constant mean across the customers and has some one standard deviation of 1. So demand is probability distribution is known, but we modeled it using robust optimization, so we have an uncertainty set, and so on. We solve this. Let's see what happens when we solve this. These are the census tracts. These are the different zip codes by their median household income. So the dark red ones are the ones which have a higher median household income. The light ones are lower. The stockouts look completely different. So what happened in my model? I just modeled what was the difference between a poor and a rich customer. The capacity of the poor customer was 20. The holding capacity was 20. For high income customers was 30. That's also something we've seen in practice. Poor people can basically afford items of smaller sizes, and the mean demand is same across the customers. But the burden of uncertainty in this simple example, it's borne by poor neighborhoods. And that's a reason for concern in inventory routing problems that actually did not specifically take into account the median household income of a zip code. And what's happening here is what is known as concentrated poverty effect. So somehow the way that the city is formed, the way that the different neighborhood and the distribution of households is placed in a city, that impacts other optimizations that you build on top of that data. And so what we did for this was we adapted multiplicative weights update, which is, I thought this was pretty cool. We adapted multiplicative weights update. We learned the right uncertainty sets so that we could have a better protection over the neighborhoods that were facing a lot of stockouts. And that gets me to my last question. Is there uncertainty in your supply chain pipeline that's impacting different segments of populations differently? Unequally, is this expected? Can you actually justify that this impact is to be expected? Or can this be mitigated with a small increase in the cost of operations? So what we saw was just increasing the number of vehicles by 1 that produced very proportionate outcomes throughout and did not increase the outcomes for the rich customers. So just by increasing 1 out of 27 vehicles. Right? So there might be a way that inequality can be mitigated by some small investment of resources. That gets me to the end of my talk. I basically presented 3 questions that were very broad, but maybe I convinced you to sort of pursue them. The first is on the Byseason data. The second one is what is fair. And the third one is the impact of uncertainty. With that, I'm happy to take questions, and I'm also looking for a postdoc and 2 graduate students to join me at the NSFAI Institute. So, thank you. I'm ahead of time.
Early, so you have time for lots of questions.
Oh no, I'm good. I thought I was ending at 10.
No, you end at 10:15.
Okay, so we have a lot of questions. Time for
Back
questions.
on
I can even go back and explain more. So yes, actually, let me take your question first. Naren's question first.
Thank you. So I like the idea of offering a portfolio of options. Seems like a reasonable strategy. But in some sense, you're really pushing the problem to the mayor, Mayor Ashcroft now. What advice would you give the mayor? So what to do with this portfolio of options? Or conversely, do you know what they actually did and how that conforms to the portfolio of options that you are offering?
Thank you, Naren. So good question. So the question is, you're actually pushing the problem to policymakers. Let me do a flip side. Would you rather have an algorithm designer take that decision and not make it opaque to the policymakers, not make it transparent?
It depends on how much you trust the policymakers.
That's also true. Okay. So I strongly believe that we need to make a lot of our modeling choices transparent. We need to be very clear about what our models can and cannot model. So the facility location example, for instance, I did not take the cost of retrofitting into account. I did not have that data. I took into account the cost of increased waiting times at emergency rooms for the nearby hospitals, and that was another analysis that I did not put in. But there could be other considerations, like Sutter Health owns which subset of these hospitals, for instance. There could be other considerations that the policymakers might have a better handle of, and by providing them a portfolio of options, we're just giving them that lever to discuss. It's interesting. I've recently been in meetings with Common Cause that actually propose or fight districting plans across the U.S. And it's the same question there. You know, it's they have questions, and policymakers, they would be like, oh, do you think this plan is not gerrymandered, or do you think this plan is gerrymandered? I could say yes and no, but I need to give them the 10 million caveats to the analysis, right? Otherwise, I might be in trouble, or they might get in trouble. So I think just making modeling decisions, data decisions, as transparent as possible. I mean, of course, we can't explain all the mathematics and all the caveats, but as best as possible, I think is a good idea.
I have a question.
Yes.
Thanks, Swati, for the great talk. I was curious. So it's very heartening that public policymakers are using fairness metrics to inform their decisions.
So they got interested in this. Yeah. They emailed us. They were like, you know, we want to chat about this, and then COVID happened, so we never found the time.
Right, but it's still encouraging that public sector is interested.
Yes.
And there is a natural interest of fairness if you are the government. I was more interested in how to make the corporations more aware and interested in this. So one of my friends is working on such a problem, and he decided to put a dollar value for the loss in being unfair. If you're unfair, you're actually losing money.
Yes.
And he tried to do that in online dating. And the company he looked into the data and he said, look, your current algorithm is unfair and you are losing clients. So should we is that a good approach, like putting a dollar value to the unfairness thing?
I think that's a great approach.
In the sense that...
I think that's a great approach. Like, I think there are different levels of approaches, right? You can put a dollar value. Right. You can say something is ethical. You can talk about the laws. You can say this is illegal. You can talk about policies. Right. And you can talk about disengagement. You can say, you know, this organization is not behaving ethically. I'm not going to engage with them.
Right.
So I think all of these tactics are good.
But it may not work out for some applications, I guess.
Sure.
Yeah. So my question is about one question you raised. So Amazon does not consider the race of the customers while delivering orders. Should it consider? So what is the answer?
Oh, so that was a news headline that I pasted there.
I see.
And you have to understand, like, there are, you know, nobody goes and writes an algorithm thinking that I'm going to discriminate against these people. It's really the interaction of the data and optimization and the decisions that you're taking that have a disparate impact, that seem to have a disparate impact. And so, you know, for Amazon's example, you can imagine that for certain neighborhoods, the baseline delivery, the demand levels were just so low that didn't make sense. But from a customer's perspective, it looked like they were having a very discriminatory outcome, right? And so one should consider demographics into account. One should consider ethics by design so that you avoid such outcomes.
Thank you. This is more of a clarification question. You mentioned that the stockout in the south of Atlanta region is more than north. Are you looking at one particular store or in general many different stores? Can you clarify on that?
This was sort of a toy example, if you will. So I just have one depot. There's just one commodity, and it's routing some demand that's actually static over customers. We did simulations to route demand that's normal products or inferior goods, where the demand would be inversely correlated to median household income, or positively correlated or static. So they're luxury items, normal and inferior goods. So we did different capacities, and we did different demand profiles, and we saw that for some cases, stockouts were just bizarre. Bizarre in the sense they were more on the poor neighborhoods and much fewer on the richer neighborhoods. And so we try to balance them using a combination of robust optimization, simulating then to see where the stockouts are, and multiplicative weights update to update the robust problem.
Okay, thanks.
Yes, Ian.
Would you mind explaining a bit more about the robust sets that you are updating? You said,
Yes.
Swati, that was a very
Yes.
cool idea, so I'd like to hear what the cool idea was. Oh, and before that, I had a little suggestion in
Yes.
terms of your, we talked about interpretability,
Yes.
and you use lambda going from 0 until infinity, which is kind of hard to explain. You could consider optimizing 1 minus lambda times efficiency plus lambda times
Right.
what did you call it? Ethical
Equity.
equity.
Yes.
Right? And then it's
Yes.
just kind of
That's a convex
weighted average
combination.
instead
Yes.
of going
Yes.
from 0 to infinity.
Yes.
So say something more, please, about the robust optimization updating of the uncertainty sets.
Right. Thank you, Jan. Excellent point. So for the uncertainty sets, we considered basically that the demand vector can be within one standard deviation of the mean. And that's the base we started with. Of course, one can do more, consider CLT kind of constraints, or consider some other maybe data-driven uncertainty sets. Okay, so we started with the very simple one, right? And then we multiplied the so you get an interval in which the demand can lie, right? And we multiplied that interval with the parameter rho. And that's a parameter that we maintain over every zip code, and we learn about how big that rho should be. So perhaps by increasing the amount of uncertainty, you're basically providing more protection to certain neighborhoods, but when you test stockouts, they look equitable. As opposed to when you have equal uncertainty sets, the inventory routing problem creates a disbalance, an imbalance in the stockout probabilities. So we are fixing that imbalance by artificially scaling those uncertainty sets.
Very nice. And was the scaling uniform over all the sets, or by each set may have their own row?
Each set has their own row. If it is uniform over all the sets, then that impact will still be there, right? That imbalance will not go away. So the row is scaled. It's like, I mean, what you would do in multiplicative weights. You have a bunch of experts. These experts suffer losses. The losses are stockouts that are given to us by an exogenous simulation, right? It could be anything else. An exogenous process gives us the losses, and we scale the row where the losses are the maximum. We multiply it by 1 plus epsilon, otherwise 1 minus epsilon.
Very good. Thank you.
Epsilon scaled by the loss. So, thank you. More questions?
Several questions online, and the
Okay.
first one is, how can fairness be used in capacity planning for a cloud server? Should it be fair, or should it be biased for the highest demand possible?
So for cloud services, and the question is about scheduling on servers.
The question is like, how can this be used in capacity planning for a cloud server? Yeah, should it be fire or should it be biased for the highest demand possible?
Mm-hmm. So again, I think it's so for let's see, for capacitated scheduling, capacitated planning on a server, you have a fixed amount of resources, and if you take resources from a group, you have to give resources. I mean, if you give resources to a group, you have to take it from another group. And so I think it really depends on the application. Like, you might have a server where certain services are just getting starved of resources because they're just such a minor quantity, minor part of your revenue at that point. But then, sort of identifying cost to not have an equitable service where you lose those growing customers, which are the smaller companies or the smaller users. You don't want to lose them, and so maybe you want to enforce some more fairness towards those. So I think it really depends on understanding what is fair, and it could be minimize maximum delay in the computations or minimize or maybe group the different services by some notion that's relevant to this application. I don't know if I answered the question, but yeah.
The second question is there any research on notions of fairness prevalent in the population? Perhaps one approach is to figure out how most people think about it and cater to this, recognizing that such an effort could be problematic in itself.
There are various notions of fairness that are studied in the literature. There is one notion that's called, so I talked about group fairness. There's another one that's called individual fairness that says that similar people should be treated similarly. So when we are thinking about hiring decisions or admissions, we want to think about maybe similarly qualified candidates should be given similar jobs, or, in admissions, or in loans, when you're giving loans to people, then you might think that, okay, similar people with similar risk profile should get similar loan amounts approved. There's also a lot of work on fairness in online learning. So how do you define fairness in a machine learning system where decisions change over time, and so it's not possible to have similar decisions for similar people because you have to learn over these population groups. And there, actually, I have some work on what we call individual fairness in hindsight. So we actually use the common notion of comparative fairness, that when I go to a store, I better get a good price compared to people who came before me, so that I don't think that I'm treated unfairly. And so we call that individual fairness in hindsight, which is a one-sided notion, and it's also being used in law in the form of precedents. So there is a lot of work that sort of goes across fields, tries to talk about, markdown optimization or the sense of fairness, what is considered fair by people. For instance, nobody minds airline tickets being priced differently, but we do mind if we are given books at a different price. Nobody minds club memberships being hiked up as some members get loyal, and there's all kinds of notions of fairness in applications in different domains.
Thank you.
Thank you. Yes?
One more. Where's the mic?
Yes. No, it's before the analysis. This picture is before the analysis. This is pretty bad, right? Because your stockouts are very imbalanced. So after everything we do, I don't have a picture for that, but after everything we do, you see the row here. Actually, do you see the stockout gap here? The stockout gap started with 1.37, which is 137% higher between two zip codes, and we got it down to 2%. So the picture is quite muted. It's almost the same color that's indistinguishable by the eye. Yeah. Thank you.
All right.
Thank you all. You've been fantastic in your questions, and thank you for listening.
Thank you, Swati.